Hello all, welcome to the video lecture. This is Ramesh Lama. In this video lecture, we will be discussing about the convolutional neural network architectures. In our previous video, we discussed about the foundation of convolutional neural network or deep convolutional neural network, where we discussed about the basic foundation or the basic foundation of the deep convolutional neural network. And we discussed about the different blocks that is used for the convolutional neural network. And today we will see some of the architectures which is that have been proposed or that are widely used for the classification purpose. And first we will begin with the LeNet-5. This LeNet-5 was developed by one of the pioneers in deep learning, Yann LeCun, in 1998 in his paper Gradient-Based Learning Applied to Document Recognition. And it was used to detect handwritten text by banks based on the MNIST dataset as fully connected networks, and activation functions were previously known in neural networks. LeNet-5 introduced convolution and pooling layer that we also saw in our last class. And LeNet-5 is believed to be the base of all other convolutional neural networks. And the architecture, it consists of 7 layers, and alternatively 2 convolution layer and 2 average pooling layers, and the 2 fully connected layers and 1 output layer with the activation function softmax. And here we can see like the input and C1, S2, C3, S4, C5, F6 and output layer. And here it consists of 3 convolutions, C1, C3 and C5, and 2 subsampling layers, S4, S2 and S4, and fully connected layer F6. And C1 to F6 layers are in C1 to F6 layers. Activation function is 10H. This architecture has used the 10H activation function. Here, if we look at the first layer, which is C1 layer, the input for LeNet-5 is 32 by 32 image, which is a grayscale image, and it passes through the first convolution layer with the 6 feature maps or filters having size of 5 by 5 and stride of 1. So the image dimension changes from 32 by 32 by 1 to 28 by 28 by 6. And as a result, we get 28 by 28 feature maps in the first layer. And the reason there are 6 feature map is that the feature map appear for each filter, and the reason the size has been reduced from 32 to 28 is because we don't see the use of padding here, or the padding is not applied here. So we can see the C1 output. In the C1 layer, we see 28 by 28 image with the depth of 6. And in S2 layer, in S2 layer, the LeNet-5 applies average pooling layer, average pooling operation, and we call it the average pooling layer or subsampling layer with the filter size of 2 by 2 and stride of 2. And the resulting image dimension will be reduced to 14 by 14 with the same depth as in previous layer, which is 6. And in C3 layer, there is a second convolution layer, which is second convolution layer with the 16 feature maps having 5 by 5 filter size and stride of 1. In this layer, only 10 out of 16 feature maps are connected to the 6 feature maps of the previous layer as shown below. We can see here. The main reason is to break the symmetry in the network and keep the number of connections within the reasonable bounds. We can see how the connection are like how two layers are connected. Like here in the table, the value 0 to 5 in the column 1, in the first column here, this column 1, this represents the feature maps in the S2 layer, and 0 to 15 in the row 1 refers to the 16 filters. This, and for example, feature maps 0, 1 and 2 are grouped and is processed by the filter 0. We can see here, like these are grouped, these are the feature maps, and these are grouped, and this is processed by the filter 0, and the feature maps 0, 1, 2 and 3 are grouped, and it is processed by the filter 6. We can see here. So in this way, the processing of the previous feature map is performed in the current feature map. And in S4 layer, like S2, it is just the subsampling step. It performs just the subsampling, and the 10 by 10 feature map image is just converted to the 5 by 5 image. We can see here. In S4, it does nothing but the subsampling as in previous S2. Previously in C3, the features like here, the image size is, feature map size is 10 by 10, and it is just scaled down into 5 by 5 image. And in the fifth layer, we have fully connected convolution layer C5, and that has 122 neuron units. And each unit of the C5 connection to 5 by 5 neighborhood on all the 16 of S4 feature maps, and that is every unit in the C5 is connected to the feature map of the S4, and thus C5 is known as the fully connected convolution layer. And the fifth is C5 fully connected convolution layer with the 120 to 120 feature maps, and each of size 1 by 1. And each of the 120 units in the C5 is connected to the all the 400 nodes, and that is 5 by 5 by 16 in the fourth layer S4. And in F6 layer, we can see it's fully connected, and it connects results of C5 to 84 units. And finally, the output layer, there is a fully connected softmax output layer with 10 possible values corresponding to the digits from 0 to 9. It has 10 output, like it the classifier, this classifier classifies the digits from 0 to 9, so it has a total 10 output which corresponds to the digits from 0 to 9. And another architecture that we are going to talk about is AlexNet. This AlexNet is considered as one of the most influential papers published in computer vision, and it has a similar architecture as LeNet, but it is more deep, and it has come up with more filters per layer and with stacked convolution layer. And it was proposed by Alex Krzyzewski on the paper titled ImageNet Classification with the Deep Convolution Neural Networks. And as I have said before, it has a very similar architecture as LeNet, but it was more deeper with more filters per layer with the stacked convolution layers, and it consists of 11 by 11, 5 by 5 and 3 by 3 convolution with the max pooling, dropout, data augmentation and ReLU activations with SGD, stochastic gradient with momentum. And it famously won the 2012 ImageNet large scale visual recognition competition by the large margin of it had the error rate of 15.53, while the architecture which won the second place, it had 26.2 error rates, and it was trained for 6 days simultaneously on the two NVIDIA GeForce GTX 580 GPUs. And we can see like the main reason for why their network split into two pipelines is it was trained with the two 580 two GPUs. And we can see here the architecture, like we can see two pipelines, and for each GPU, and it contains 8 layers with the weights. The first 5 are convolutional and the remaining 3 are fully connected. We can see here. And the output of the last fully connected layer is fed to 1000-way softmax, which produces a distribution over the 1000 class levels. Means it can classify the given input into one of the 1000 categories. Like the classification range is very high as compared to the Lineage 5, as Lineage 5 had just 0 to 9 or 10 classification range, but class level was just 10. But here this classifier can classify 1000 class levels. And in first layer, the convolution window is of shape 11 by 11. We can see here, like in the input layer, it performs the classification of 11 by 11 size, and the convolution window shape in the second layer is reduced to 5 by 5 followed by 3 by 3. And in addition, after the first, second and fifth convolution layer, the network adds maximum pooling layers with the window size of 3 by 3 and stride of 2. And after the last convolution layer, there are 2 fully connected layers with the 4096 outputs. Like each individual layer has 2048 and altogether 4096 outputs. And finally, at the output, we can see 1000 classes. And the kernel of the second, fourth, and fifth convolution layers are connected only to those kernel map in the previous layer which reside in the same GPU, which also can be visible here in this architecture. Like the second and fourth and fifth, these convolution layers are connected to those kernel maps in the that just in the same pipeline. They are connected to the in the same pipeline, and the kernels of the third convolution layer are connected to the all kernels map in the second layer. That can also be seen here, like this figure shows. And the neurons in the fully connected layers are connected to all neurons in the previous layer, and ReLU is applied after every convolution and fully connected layer. And here is another method, dropout is applied before first and second fully connected layer, and we will discuss in more detail about dropout in our subsequent slides. And the network has total 62.3 million parameters, and it needs 1.1 billion computation units in the forward pass, which shows like how complex this architecture is. And there is another term or another method that they have implemented is max pooling. And here the max pooling is they have used overlapping max pooling that we have discussed in our previous classes as well. Like the max pooling layer are usually used to downsample the width and height of the tensors, keeping the depth same. And overlapping max pool layers are similar to the max pool layers, but the adjacent windows over which max is computed overlap each other. And the other authors used pooling of size 3 by 3 and a stride of 2 between the adjacent windows. So this overlapping nature of pooling helps reduce top 1 error by 0.4% and top 5 error by the rate of 0.3 respectively, when compared to using the non-overlapping pooling windows of size 2 by 2 with the stride of 2 that give the same output dimension. So they have used the overlapping max pooling of size 3 by 3 with the stride of 2. And another feature of the AlexNet is the use of ReLU. As we have discussed about ReLU in our previous classes, like tan-edge or sigmoid activation functions used to be very usual way to train neural network model. But the AlexNet showed that using ReLU non-linearity, deep CNN could be trained much faster than using the activations like tan-edge or sigmoid. And here we can see from the figure that using the ReLU, AlexNet could achieve 25% error rate and 6 times faster than the equivalent network using the tan-edge, which we can see here. And other is this was tested on the CIFAR dataset. Now other thing they have cared about is the overfitting, and to reduce the overfitting they have used two methods, like one was the dropout and another one is data augmentation. And while talking about the overfitting, this is one of the problems that occur during the neural network training, and the analogous of this thing is of overfitting is like we try to memorize the examples in the training data, but without understanding the concept. Just try to memorize and without understanding the concept. So what happens is, like when training a model by updating each of its weight, it might become too dependent on the data set we are using. So this will result in the error on the training set is driven to a very small value. Like this will give the training error very low, but when the new data is presented to the network on testing, the error is large. Like it may work for some specific pattern of data, but when new pattern of data is introduced to the network or introduced to the model during the testing, the error is very large and the model doesn't work well for the new set of data. So the author of AlexNet reduced overfitting using a couple of different methods. One was the data augmentation, and the showing a neural network different variation of same image helps prevent overfitting. And here we are forcing it not to memorize, and often it is possible to generate additional data from the existing data for free. And here we can see some tricks, and one is like generating the mirror image from of the same image. We can see here the mirror image. We can create mirror image. Another one is just random crops from the same image. We generated 4 different images with the cat located in the different location. And other ways of data augmentation is like rotation, that also creates some new form of data, a new form of image. And another is with the dropout. With about 60 million parameters to train, the authors experimented with other ways to reduce overfitting too. So what they did was they applied another technique called the dropout, and it was introduced by the Geoffrey Hinton in another paper in 2012. So this dropout is also one of the technique. It is used for regularization, and the basic idea of this method is to, based on probability, we temporarily drop out the neurons from the original network. Like we can see here in the figure, in the standard neural network, all neurons in the space, some particular layer is connected to all the neurons in its previous layer and its next layer. But in dropout, what we do is we drop some of the neurons, or we deactivate the neurons, and doing this for every training example gives us the different model for each one. So afterwards, when we want to test our model, we take the average of each model to get our answer or the prediction. So we assign, while training the model, we assign P to represent the probability of neuron in the different layer being excluded from the network, and this probability is usually equal to 0.5. And when a neuron is dropped, it doesn't contribute to either forward or the backward propagation. So every input goes through the different network architecture as shown in the figure. But while the testing, an output given from the model trained using the dropout technique is a bit different. What we can take a sample of many dropped out models and compute the geometric mean of their output neurons by multiplying all numbers together and taking the product's square root. However, since this is computationally expensive, we use the original model instead by simply cutting all of the hidden units weight in half. Like what we do in the testing is we take all the weights and we simply multiply the weights by 0.5, or we scale it by 0.5. So this will give us a good approximation of the average for each of the different dropped out models. So in this way, the dropout is implemented in a different for the regularization or to reduce the overfitting of the model. And this is the visualization of AlexNet layers. Here we use the 96 convolution kernels of size 11 by 11 by 3 learned by the first convolution layer on 224 by 24 by 3 input images. And the top 48 kernels were learned on the GPU1, while the bottom 48 kernels were learned for the GPU2. And while we look at the top 48 kernels, this looks like it is highly selective to the orientation. Like it will select only the input which are of particular orientation. Like each kernel is associated with some orientation in some specific direction, some certain direction. And while we look the bottom 48 kernels, like it looks for the frequency and color selective, and this will pass only this filter, or this kernel will pass only the specific color or the image of some specific frequency. And if we compare it with the structure of the visual cortex, it is found remarkably similar with the structure of the visual cortex.